Hi everyone. So in this lecture, which is the last lecture of the course, we are going to cover two topics, quadrature and interlacing, and then as a corollary, prove the existence of Ramanujan graphs or one-sided or Ramanujan graphs of every degree and every size. But it's actually kind of a longer, in terms of lectures, it's maybe one and a half lectures, like 4.5 hours rather than the 3 hours, but we'll see. Um, so in the last lecture, we talked about the R transform and we proved the bound on the R transform of the additive convolution in terms of the R transform of the individual marginal distributions that we started with. And in this lecture, we're going to do quadrature, which is a way of translating the all orthogonal orthonormal matrices that we are looking at currently, which are expectations in terms of integrals because they are continuous, to expectations of permutation matrices. This is great because permutation matrices are preserved the graph structure. So if you start with a graph, you end up with a graph, just permute the vertices. What's not clear is why permutations are kind of sufficiently random to behave like random matrices, but that's the kind of real magic in what we are going to see today. Okay, so let's get right to it. And again, also this part is based on this interlacing families 4 paper of MSS. Okay. So as I kind of hinted, the main theorem that we are going to prove in this unit, we are going to have 3 units in this lecture, this interlacing and the existence of Ramanujan graphs, but in this particular unit, the main result is what's called a quadrature result. A quadrature is a general name in some communities that talks about writing integrals in terms of sums, finite sums. And that's what we are going to have today because how random uses integrals, whereas taking the expectation over the permutation group, although it's large, it's still finite. Okay, so the technical theorem that we are going to prove, which we'll call the quadrature for the additive free convolution, is the following. Say you have two D by D symmetric matrices, A and B, and from here on we are going to assume our matrices are real valued, so symmetric matrices instead of Hermitian. All of them are going to have real eigenvalues also, right? Okay, with potentially different eigenvalues, but is an eigenvector of both of them. Um, so in this case, right, the characteristic polynomial of A and the characteristic polynomial of B can be written as you can factor this little a or respectively little b eigenvalue and write the characteristic polynomial of A as x minus A times some other polynomial, this time of degree d minus 1, it's also real-rooted, and same for B. And the corresponding polynomial here is going to be denoted by q of x. Okay, then what the theorem tells us is that the expected characteristic polynomial with respect to the permutation group SD is the same as, okay, so you have this factor of x minus a plus b, which is expected because every polynomial here has has x minus a plus b, sorry, has a plus b as an eigenvalue because it's the same eigenvector in both cases that gives you this sum of eigenvalues. But, other than that, or in a sense orthogonal to that, the other factor in this expected characteristic polynomial in terms of mutation is the d minus 1 additive free convolution, which, if you think about it, if you recall by our definition, our original definition, not the more general one, is really what it means is that, orthogonal to the all one eigenvector, you do a completely kind of Haar massage to the eigenvector structure. So you shuffle everything orthogonal to the all ones eigenvector. Okay, so that's the theorem. I mean, right? You have the all ones vector built in. It has some built-in structure into the matrices, so you cannot expect things to be completely shuffled, but under these assumptions. So orthogonal to that, what this theorem tells you is that permutations are as random as how. Okay, And I should say, in terms of graphs, and this is the content of this slide, the assumption that one is an eigenvector just means that the matrix is the matrix is just as a matrix corresponding to a graph, which is regular, right? Little a regular in the A case and little b regular in the B case. We are going to handle regular graphs, so for us it doesn't really matter. And the other, so you can look at this slide, this paragraph here. This is what I just said, and the other paragraph is what I said before about Haring permutation being the same, orthogonal to the structure of all one's eigenvector. So let's see. So the start of the beginning of the proof is actually what everyone will probably do, given the statement. So first of all, you want to walk orthogonal to the all one's eigenvector. And by basic linear algebra, just to have a nicer representation, you can always find an orthonormal matrix V such that VA transpose is of this block structure, where you have D minus 1 by D minus 1 matrix A hat. And the last block, the second block, is just one entry little a. Really what you're just doing a base switch in which one is mapped to En or vice versa, depending however you multiply from left to right. And we denote this matrix by A hat, this nice cool plus little a. And the same V can actually be used to diagonalize B in that block structure, because also B, the matrix B has 1 as an eigenvector, the all ones as an eigenvector. So the same V can, using the same V by conjugating or transpose conjugating B by the same V, you get the same block structure with some B hat. Or put differently, right, you can simultaneously diagonalize both A and B because of the common eigenvectors that you have. And with this, what you can do is, let's massage a little bit the left-hand side that we had in the theorem, namely the expected characteristic polynomial with respective permutations. So, right, we can always multiply by V and V transpose from both sides, because you can always shift V transpose here, and then it just goes away, and you can shift it because the characteristic polynomial is cyclic. And then distributing V to A and to the PB transpose. So to A, you'll get this VA V transpose, which we called A hat plus A, like direct sum A. And let me also insert, like, between the P and the B and the B and the P transpose, also an identity which we'll write as V transpose V. That's what's written here. So that in the next slide, by putting the brackets in different forms, you get this expression. This is what we had before, and now instead of bracketing V transpose and V like that, I'm actually bracketing it according to I'm kind of conjugating P, B, and P. Okay, so with this, now that we kind of conjugated P, B, and P transpose here, we also know that 1 is also an eigenvector of P, right? Because P is just a permutation, and the corresponding eigenvalue would be 1. So you can also write V transpose. I mean, V transpose is of the form P hat at D minus 1 by D minus 1 block, and times 1 at the bottom right entry. And P hat is some matrix. We'll talk about it in a second, but it's some matrix for now. It's you'll see, we'll understand its geometric interpretation in a second, but let's just call it P hat. So what we have is that the original expected characteristic polynomial that we had with respect to permutations can be written like that. So you have these A hat plus A, and then you sum up these P hat plus 1, plus is a direct sum. And then B hat plus 1, P hat plus 1, then transpose. And then you can also insert the transpose inside, like we did here. And note that this expected characteristic polynomial that you have here is actually, you can pull out an x minus a plus b factor, or really an x minus a plus 1 times b times 1 factor. because this gives you the A and this gives you the 1. So this one, this is, oh, this should be a B, sorry. And this is a 1. And so you get this x minus a plus b factor, which we talked about, and we expected it to have it. We just change basis to kind of work more easily with the remaining part. But so that's we knew should come. And the other part, the interesting part, is the expected characteristic polynomial of like only the hats. So a hat plus p hat, b hat, p hat transpose. And I think I'm implicitly using the fact that p transpose hat is p hat transpose, but I'm not sure, and that's still true. Okay, so we are looking at this polynomial. So we kind of factor this polynomial as the obvious part and this part, which we should understand now. And to understand it, we really need to understand what p hat does, and it's kind of neat. So there are words here, but I think the better thing to do is to look at the picture. So what p hat really does is the following. So p hat works orthogonal to the all ones vector, and you can ask what does it do to the basis elements E1 up to En or Ed in our notation. And actually, again, it works orthogonal to the all ones vector. So the actual question you should ask is what does it do to the projections of E1 up to Ed orthogonal to the all ones vector. So this is the picture you should have in mind. So here I took D to be free, and this is the all ones vector sitting here. And unless I did something wrong with plotting this, E1 hat, E2 hat, and E3 hat are exactly those projections of E1, E2, and E3 orthogonal to the all ones vector. So you see it lies on a plane, dimension 1 less, of course, because you reduce to dimension d-1, and not only that, it's the d-1 dimensional subspace orthogonal to the all ones vector. And it requires a little bit of either calculation or self-convincing, but it's kind of obvious and intuitive that what p hat does, it does exactly what p does, but to these projections. So if p maps E1 to E4, because the permutation acts like that, then p hat will map E1 hat to E4 hat. Okay, so it kind of shifts like that. Say maybe you had the cycle permutation, 1 goes to 3 goes to t. Then that p hat will preserve this permutation structure, but it will work orthogonal to the all one eigenvector. Okay, so that's what p hat does to. In that sense, p hat encodes the permutation in that it permutes in the same way the hat versions of the standard eigenvectors. Okay, and from here on, actually, we are going to work with d-1 by d-1 matrices, and they are denoted by a hat, p hat, and so forth. But we're not going to care about a and b anymore, and so we're just going to write a for a hat and b for b hat, and also we're going to write d for d-1. So we're kind of reshuffling the notations and talk about a, b, and this is in dimension d. And also, right, in the determinant that you get by considering the characteristic polynomial, you have this xi minus factor, which you can just kind of swallow inside a. So instead of talking about xi minus a minus p or p hat b p hat transpose, we are just going to swallow the xi minus a to just an a. So really, a is going to be xi minus a hat in the previous notation. And all of this is just to say that we are going to prove this star, which immediately implies what we want. What we are going to prove is that if you give me any d by d symmetric matrices A and B, and again, this d is actually d-1, and A and B are actually xi minus a hat and b hat respectively, but don't worry about that. What we want to prove is this thing. We want to prove that, so if you look at the determinant of A plus P transpose, so no chi of X because Xi was swallowed into A, and the minus also, and B is actually minus B and so forth. Then if you take the expectation over AD, which I'll talk about in a second, that's the same thing as taking the expected characteristic polynomial, expected determinant, sorry, old habit, with respect to the Haar unitary or Haar orthonormal matrix Q. And AD is exactly what you think is the, I think I wrote it here, AD, or here it's AD minus 1, it's before we switch to D, is the group, the symmetry group of these points, E1 hat, E2 hat, E3 hat, namely all permutations that maps E1 hat, E2 hat, E3 hat as a set to itself, right? The vertices are kept, are mapped to the vertices, not every vertex to itself, but the vertices are mapped to the vertices. That's the definition of a symmetric group of this set. And generally this set, if you think about it for a second, it's the structure of a regular simplex. I'll remind you what that is, but it's essentially a generalization of equilateral triangle or a tetrahedron in general, in dimension 3 and then in general. So let's see what I'm talking about here, actually. Maybe this is the right point to do it. So what's the regular simplex? So the regular simplex of dimension D has D plus 1 vertices. And the first few examples are as follows. So dimension 0 is just a point, right? So dimension 0 has 0 plus 1. So 1 point, 1 vertex. In dimension 1, you have 2 points. So the regular simplex has 2 points, 2 vertices, and they are connected by an edge. They are in distance one of each other, of one another. Dimension 2 is just the equilateral triangle, right? You have 3 vertices now, and they live in 2 dimensions. And these are the vertices that have the property that the distance between every pair of them is 1. And in dimension 3, you get a tetrahedron, right? You have like this pyramid, very symmetric pyramid. And inductively, if you want to construct the dimension n regular simplex, you start with the dimension n minus 1 regular simplex, embed it in a higher dimension, like you put this here in 3D, and then you take a point that has distance 1 for all the vertices that are already there. So this is what you did from here to here, right? You added, so you took the point, consider it in 1 dimension, and then took one of the 2 points that you could have taken of that to be of distance 1 from that point, and then you took that line and you had 2 choices again for which vertex to add, but it doesn't really matter, to be of distance 1 from all the points that were there. And also here, right? You started maybe with this triangle, and then you had 2 choices, up or down, like that, to be of distance 1 from the 3 existing vertices, and so forth. So this is the construction of the regular simplex. And you see in this picture, for example, you see the triangle. That's the best I can draw here. I can do one more dimension, but then like the all ones vector will sit in the fourth dimension. So I don't know how to draw this. So that's the structure that you have, because the distance between all of them are the same, and they sit in an n minus 1 dimensional thing. And the simplex in this case is kind of centered at the origin. Okay. So again, star just tells us that taking the expectation of a permutation in the symmetric group of AD, which we'll need to understand, like the symmetric group of the regular simplex, centered at the origin, is as random as Haar unitary or Haar orthonormal in this case. So in order to prove star, we are going to, star is a quadrature result, right? It tells you that some integral equals some finite sum because the symmetric group of AD is finite. And in order to prove this quadrature result, we are going to prove a stronger statement. We are going to prove in a sense, an invariance result, which generally, in general terms, but I'm going to be specific here, implies quadrature results. So lemma A here is a lemma that tells us that if you prove an invariance result, you get a quadrature result for free because it's a stronger statement. So I could have written it like for general groups and so forth, but let me be more specific. So let's say you have a function, and our function in this case just it's going to be some determinant and so forth, but a function that takes any elements, any orthonormal metrics in the dimensions to the reals. Okay, and you can kind of look ahead here and see that the functions that we are going to take will map P to the determinant of A plus PB transpose, but never mind that for now. So you have this function, and say you're looking at some subgroup H of this OD, right, of all orthonormal matrices. In our case, H is going to be AD, of course. So that's what's written here in the future, but again, never mind that. And assume that you can prove the following. Assume that you can prove that for any Q0, any specific orthonormal matrix, the expectation of F on H, namely you sample P from H and take apply F to it and then take the expectation, is the same as if you take the expectation of P times H, namely you sample from H, multiply from the left by P and evaluate. So that's kind of an invariant, right? For F, it doesn't matter if you take the average over H or over some cosets of it. Then in that case, what you immediately have, and that's a one-liner, is that the expectation of F on H is the same as the expectation of F on the entire group, OD. Okay, so why is that? Well, starting from the right-hand side, because Q, by its definition of hardness, is that if Q is hard distributed, then also PQ is hard distributed for every P which is orthonormal. That's kind of the characteristic definition of hard. Then you can put a little P here, right? It doesn't really matter. It doesn't change the distribution you average over. So that's what I did here. But then I also took the average over all P and H, right? It works per P. It definitely works on the average. And then if you just switch order of expectations, you have the expectation over Q outside, but inside you have the expectation over P and H of FPQ. And per our assumption of invariance, you can just remove the Q. Right? It doesn't matter which coset you average over. And once you remove the Q, you can also remove the expectation over Q, and you get the left-hand side here. So one-liner, as promised. So to prove star, instead of proving a quadrature result for respect to AD, we are going to prove an invariance result. Namely, we are going to prove that for every Q0 in OD, taking H to be AD and F, as I said, to be this determinant, it's actually F of A comma B, but let's just call it F. We are going to sometimes write A and B explicitly because they are going to change in the proof sometimes, but generally just ignore them. So we're going to show that with this H and this F, the invariance holds and therefore quadrature holds. So the strategy will be to break down in terms of writing the group as a product of generators, but break down the groups that we are looking at, which is OD and AD, like it's finite subgroup, I mean, you don't have to believe me, it's finite. It's going to be part of the proof, but we are going to break it down to like two-dimensional phenomena, right? So let's look at. So this tetrahedron, what will happen is that we are going to work on the faces in a sense, right? We are going to say that any element in OD and also any element in AD, namely a permutation of the vertices here. So what we are going to show is that what we are going to understand is how they work like per surface or per two-dimensional kind of face of the simplex. And then we are going to use a general result that tells us that well, once you understand what happens in these faces, because you can write any element in these groups we'll talk about that more specifically, but as a product of elements operating only on the faces, leaving the other vertices intact, you get the general result. So the idea is going to be to reduce it to degree 2, to dimension 2, sorry, and understand it completely, and from there deduce the general case. So let's start doing that. So we need some notation. So given 3 vertices of the regular simplex, maybe EI hat, EJ hat, and EK hat, we are going to denote by AIJK the subgroup of AD that permutes these 3 but makes that where the other vertices are fixed, right? So these are all the group elements that may permute I, J, and K, or their hat versions among themselves, but any EL for L, not I, and J, and K must stay put. Okay? It's a fixed point. Right, so you will talk about it, but you can imagine you can kind of rotate, right? And you can also reflect around some origin, some line. Maybe you can see it from the picture, right? So here, so say you want to consider this 3 point, this is EI, EJ, and EK, and you want to keep this point fixed, right? So you can do that. There are permutations that do that, because you can always kind of rotate this plane that they sit on in 120 at 240 degree angle, while remaining the other elements fixed. In this case, it's one element. Or you can also reflect around this or that lines. So intuitively, at least, you can see that AIJK is really just the symmetric group of this thing, and so forth. And also, in terms of the orthonormal group, let's denote by OIJK rather than AIJK all the subgroup of OD, which does the same thing. So it fixes all of the other EI hats, but it can do whatever it wants. Like it can do O2 really to the subspace or affine subspace in which EI hat, EJ hat, and EK hat lives in. Okay, so this is really just O2. You just have whatever you can do in the plane to have of a normality, and this includes rotation, but not only in 120 and 240 degrees, but any rotation, and also there are reflections. We are going to talk about them. So what do we know? So definitely the IJK version of A is a subgroup of the IJK version of O, right? Because every element in AIJK satisfies the requirement of OIJK. It's stronger, right? Because the vertices of the 3 vertices that you are looking at actually maps to themselves as a set, which is not required in OIJK. You just need to be in the same subspace. And as I said, AIJK and OIJK are just isomorphic to A2 and O2, respectively. So the lemma that we want to prove, and that's the main lemma here, given that the invariance implied quadrature lemma, is that there is an invariance for A2, or for this kind of isomorphic version of A2. So it's A2, but where you are looking at this subspace of 2 dimensions in d-dimensional vector space. So what we are going to prove is that for d by d symmetric matrices A and B, and for every Q in O2, like for every fixed element in the larger group, so the expectation here, where you take P only from A2, and that's the expectation of what you kind of expect, is the determinant of A plus, now you should come PB, P transpose, but P is, right, there is the interesting part and the non-interesting part. And for simplicity here, I'm kind of assuming and taking IJK to be on the corner, maybe like 1 to 3. So P can be written as P plus ID minus 2. So that's kind of the usual direct sum. And P P is the thing that actually operates in 2 dimensions on the three vertices. Okay. So you conjugate B by P plus I and then P plus I transpose, of course. When the claim is that this is the same as the same thing as if you just kind of push a Q0 here after P. Okay, that means invariance, right? A2 doesn't matter if you ever do. I mean, this function doesn't matter if you average according to A2 or any of its coset from O2 for as determined by Q0, general element in O2. Okay, so that theorem will essentially imply what we want. It will imply it for one phase, but then you can use a general result that tells you that OD and AD, both for their own reasons, are generated by elements from O2 and A2. So let's see. Let's see why this lemma is true. Let's denote by FAB of M. So that's slightly different than what I said before. FAB of M is the determinant of A plus M plus I. So M is 2-dimensional, right? M plus I, this is ID minus 2, but I don't want to ID minus 2 time. B M plus I transpose. So let's consider this function. This is the actually function that we have here. For M, in this case, it's P, and in the other side, it's PQ0. And with this notation, we want to prove what we'll call a two stars. And 2 stars asks you to prove that for every Q0 in O2, it's just a notation, the expectation of F according to A2, which is really what's written here, is the same as the expectation of F as according to A2 times Q0. But that's what you want to prove, essentially. And in order to do so, you really have to kind of dig in and understand how A2 and O2 looks like. And all the mumbling I always mentioned at the beginning of the course about how is essentially, rotations and reflections. What I really meant is this thing. I meant it's rotation and reflections in 2 dimensions, and then these are the generators, and then you compose. So what do I mean? So let's go over slowly. So let's look at SO2. I'm not going to use that notation much, but SO2, that's the subgroup of O2 corresponding only to rotations, right? Not reflections. So really the matrices here are parameterized by theta, some angle between 0 and 2 pi. And the matrices can be written very explicitly. I'm sure you've seen it at some point in your life. And let's also consider the subgroup of reflections, right? So that's just a size 2 subgroup. It's finite. And it's generated by, let's say, reflections around the horizontal axis. Right? So this matrix H for horizontal is reflections around the horizontal axis if you consider the first coordinate as X and the second as Y. And the generated, I mean, that's an involution. So if the generated subgroup is just H and the identity, one other subgroup that we introduce is this subgroup. So let T be the angles that I was talking about, 2 pi over 3 and 4 pi over 3, 120 and 240 degrees. So let Z3 be the subgroup of SO2 and also of A2 that contains these rotations by these angles, right? So 1/3 and 2/3 identity. So this is a subgroup of rotations. It's a subgroup of A2 also, because that's all the rotations that you can do in order to put the vertices back in place. So the 2 facts that I'm going to use, these are easy geometric facts, and that's what I really meant when I said that reflections and rotations are what you have in R and in our case in AD. The following 2 facts are the following. So O2, you can decompose it as either do a reflection or not, and then do a rotation. Right. So any element in O2, any unitary matrix in 2 dimensions, it's just either you reflect or not once, and then you choose how much you want to rotate. You can think, you might ask, maybe you should need to reflect again to get the whole thing, but no, we'll see that. Okay, so O2 is composable in this way. And similarly, A2 is Z3 times D, right? The same thing. So you can choose either to reflect or not. And then you can decide in which of the angles to rotate, 120, 240, or do nothing, which is 0. And once you have this, the first thing you're going to do is to prove what we call free stars. So free stars is not exactly what we want to prove, but it's a step towards it. It shows you that it gives you an invariance with respect to r theta, namely, and with respect to Z3 also. So it's kind of so it tells you that F, which hides also A and B, as I said, the expectation of F under Z3 is invariant to multiplying by r theta. Okay, so you get Z3 or you get Z3 r theta, the same thing. So it's a kind of a weaker and stronger statement. It's weaker because it's invariant only to r theta. You don't have the reflections. You want to be invariant to A2 in general, to O2 in general. This is kind of half of O2 in a sense. But you use less randomness, right? So you only average on Z3 rather than on A2. So it's an incomparable statement, really, but we need it in the proof. So that's what you're going to prove first. So let's see why is this true. So let's look at the right-hand side. And this expectation is just a sum of three elements. So let's look at 3 times this number, so we won't have to carry this 1/3 all the time. So this thing times 3 is really you sum over all tau in t, right? Because Z3, if you remember, is just R0, R120, and R230 degrees. So you're going to take the sum of F, apply to R theta. Theta is the sum that we're running over, times R tau, times R theta. And R tau times R theta is just R tau plus theta. Right, so the right-hand side here is just this sum. You sum over 3 angles. F applied to our 3 angles. And a lemma that we are going to defer its proof tells you the following. Okay, and the lemma that we are going to prove, which we are going to defer, is that for any symmetric matrices A and B, D by D symmetric matrices, F AB of R theta is a kind of a low degree polynomial in not quite polynomial in e to the I theta, or more precisely, F of AB of R theta can be written as a sum where you have 5 summands, and they're corresponding to, there is some constant that depends on A and B, and then that constant, that CK, goes between -2 and 2, and the corresponding term that multiplies it is e to the ik theta. So what I'm saying is that you can always write f of r theta as some combination of e to the ik theta for the case between -2 and 2. Okay? And we'll see why that's true later, but let's continue on. So 3 times the right-hand side of 3, and this is 3 if you kind of forgot, 3 times that is, well, we sum over all t and t, so that's what we had here. You sum over all tau in t, and you look at f of r tau plus theta. But f of r tau plus theta, according to lemma 3, you can write it like that. So there are some c minus 2 up to c2, multiplying e to the ik now tau plus theta. That's per t, per tau. And now you can switch the order of summations, and you actually write sum from k minus 2 up to 2, ck, and then I'm going to actually explicitly write the sum, the free summands, and taking e to the ik theta, factor it outside, like this. This is common to all, just the tau changes. So what you're left with is this sum, which is just sum over all, e to the ik 0, e to the ik 120 degrees, and 230 degrees. And we know that a sum like that has to be 0 unless k is a multiple of is divisible by 3, right? Because this is the sum of 3 units vectors raised to the k. So the only way it's going to be non-zero, and in this case it's going to be 3, is if k divides 3 and each of the summands is divisible by 3, and each of the summands is actually 1. But k is between -2 and 2, kind of interestingly. So that's not the case. And this means that the only way that this can happen, the only way that this is non-zero is when k is 0. Right? K doesn't go up to 3 or -3. And when k is 0, you only have like C0 times 3 here, because this is 3, this is 1, and this is C0. Okay, so what we just proved is that 3 times this thing, the right-hand side, is actually independent of theta. We get just 3C0. C has nothing to do with theta. That maybe I should have expressed that. So, I mean, the only dependence on theta according to lemma C is in this e to the I k theta. Ck is independent of theta. Yes, I mean, it's implied because of the way the quantifiers are written there. But so in particular, it's the same expression also for theta equals 0. And for theta equals 0, you just get the left-hand side, right? Because you multiply by R0, which is 1, the identity. Good. So we actually proved, using lemma C, we proved 3 stars. Okay? So we just proved this thing, that there is some sort of invariance, namely Z3, if you take the expectation according to Z3, but you take any coset, which is a rotation, not necessarily a reflection, then you get your invariance. Okay. So the next step we're going to be to prove 4 stars. That's the last. We won't see 5 stars. So in 4 stars, we are going to still work with Z3. Okay. But we are going to extend what we proved, and we are going to prove that F is invariant. So we're actually going to prove that Z3H is invariant under R theta, right? Because you're going to sample P from Z3, and on one side you're looking at PH, and from the other side you're looking at PH times R theta. Okay, so how do you prove that? So it's kind of related to what I said before. First, we observe that H R theta is R minus theta H. So H and reflection and rotations do not commute, but in a sense they do. So they commute, but you need to reflect theta back to minus theta in order to get the equality. So that's why you don't need H R theta and another H or something like that, because you can always push all the H to the right or to the left. So first of all, we observe that. That's an easy exercise that you can do. It's very elementary. So this means that for every P in Z3, I mean, I'm not looking at the expectation, only on the fixed P. If you look at the thing on the right hand side, and now I do want to stress what A and B are, because they are going to change. So FAB for fixed A and B of PHR theta, well, by definition, it's just the determinant of A plus, and then you have these 3 matrices, sum of I, then you have the B, and then you have the transpose of the thing from before. And the point is that now you can decompose this PHR theta. So first of all, you can push H to the right and get a minus theta here. And then secondly, let's push H or H plus I and write it as part of B and actually be left here with PR minus theta. Right, so you get the determinant of A, and then you get PR minus theta I. The minus is because you flip the H and the R theta. And then you have HI, which is kind of pulls, you can obviously do that. But I wrote it suggestively, conjugating B. And let's call this thing beta prime. Okay, so if you call this thing beta prime, this H plus I, B, H plus I transpose, then the thing that you are looking at is actually exactly F of AB prime of PR minus theta. Now, if you take expectations, as we have in the right-hand side of 4 stars, then instead of taking the expectation of f of AB pH r theta, because of that, it's the expectation of f of AB prime PR minus theta. And free stars allows us to just remove the r minus theta. Right, because free stars, if you recall, let's recall, that's the recall of free stars, tells you that Z3, expectation over Z3 is invariant under rotation. So you can just remove the rotation from the expectation and get the same thing. So I just remove the rotation. So I got this thing. It's with a different B maybe, but the the proof works for every B prime or B which is symmetric, and B prime is certainly symmetric because B is, and then you multiply by H, and H transpose with I is there. Okay, now let's open this up a little bit just so that we can see this. So what is this expectation now? Well, it's the same expectation, but the inner thing is the determinant of A plus. And now I'm taking the B prime and writing it as B, but putting back H back with B, now that R minus theta is gone. And if you stare at it for a second, it's exactly the left-hand side that you wanted to arrive to. Right, because it's f of AB now applied to pH, no theta. Okay, so a quick recap. So we proved two things. We proved 3 stars and 4 stars. 3 stars tells us that Z3 is invariant under rotations, and also Z3 times, this is 4 stars. Now Z3 times H is invariant under rotations. And that, the next thing we want to prove, but it's a corollary now, is that 2 stars, that's what we want to prove, namely that A2 is invariant under O2, not just rotations. So we have more randomness, so it's easier to prove because of that. A2 is more random than Z3, but Q0 is more general than theta. Okay, and of theta H, but not really, because R theta H and R theta is essentially all of O2. And that's really the proof. But okay, so let's see. So as A2 is Z3 times F, namely every element in the symmetric group of this equilateral triangle is, you either or not do a reflection and then you do a rotation in 120 or 240 or do nothing to what you got. Because of that, we conclude from what we just showed, what we saw, is that for every theta, A2 is, there is an invariance of A2 with respect to R theta, right? Because A2 is either this thing or that thing, right? Every element in A2 is either a Z3 element or a Z3 times H. So even these kind of partial expectations are the same. So certainly if you take the expectation of them, you get the same result. So this proves two, which for which Q0 is just of the form R theta. And so to conclude the proof, we want to also consider what happened if you plug instead of R theta times H, right? And then that will be the end of it, because every matrix in O2 looks either like R theta or R theta times H. So namely, this is what you want to prove. Theta if you want. For theta, A2 is invariant under R theta H. But that's really follows by what we did, because the expectation on the left, it's kind of easier to put it to start from on the right, to start with R theta and H and then remove it rather than adding it. But the expectation on the right is the same as the expectation where you again flip H and R theta to get H times R minus theta now. So that's what we have here. That's this equality. And now the point here is that A2, it's more random. So sampling P from A2 and then multiplying by H, it's the same thing as A2. Right? It's the same distribution, because in half the time you reflect first and half you don't. So you just reflect again, which is an involution. So this means that this equality holds, because if sampling P from A2 and putting H or not, it's the same thing, same distribution. And then 2 star theta or minus theta tells you that you can just remove the R minus theta. That's what we proved before. And therefore you got rid of both the h and the r theta, and you're done. That's the left-hand side that we have here. That proves lemma b. And as a recap, we want to prove a quadrature result for the additive free convolution. We started with kind of the main idea in which we don't prove quadrature, prove invariance. So lemma A tells us that it's enough to prove invariance, and that's actually was the mindset for the proof. And using a lemma that we still need to prove, we proved lemma B, which tells you that there is an invariance of A2. Now, I'm going to omit the claim that once you have that, you have invariance of AD. That's a general fact that once that AD and also OD are generated by A2 and O2, that's, you can see the proof in MSS. They were kind enough to put it there, but it's a standard fact. It also appears in Wikipedia. And it's not quite an induction, but it's a kind of iterative process in which once you have this product of generators, invariance under each generator implies invariance of the entire group action. Good. So really the remaining thing to prove is lemma C. Once you have lemma C, you are done. So this is lemma C, just a reminder. So lemma C tells us that for any d by d symmetric matrices, there are numbers that depend on the matrices, such that, like 5 numbers, such that f of AB of r theta, where f of AB is this determinant, the dependence on theta is very simple in a sense. It only depends on e to the ik theta for k, which is between -2 and 3. It's kind of a low degree dependence in some sense on theta or e theta. There are also minuses there, so okay. So let's look at the proof. It's short, but it's in a sense it's much of what's going on here. It really that point. I think it's this point in the proof mostly, not only, but mostly, that the function itself, the fact that it's the determinant of something plus something, it doesn't use all the information of A and B, just this determinant of A plus something B something that plays a role, right? So this is in pseudo-randomness perspective. Here we use the fact that F is in a sense simple. It's computationally weak. It can't look at the entire A and B as it wishes. Okay, but okay. So to start the proof, let's note or recall that you can simultaneously diagonalize all 2 by 2 rotation matrices. Namely, the rotation matrices look like that, as we said, but you can write them as U ei theta e minus I theta U conjugate, where U is independent of theta. Okay, U is just this matrix. Okay. You can convince yourself of that just by opening it up, but there are smarter ways of arriving to that. But, in particular in our case, R theta plus ID minus 2, you can also write it like that. So you have now d-dimensional matrices V d theta and V conjugate, where V and V conjugate are independent of theta. They just come from U when you just add ones where you should in the diagonal. And d theta is the same. It's just the diagonal matrix that you had here, but you put the ones in the remaining of the diagonal. So d theta has dependence on theta, and V doesn't have dependence on theta. That's what you really need to remember. Well, you also need to remember how d theta looks like, but so let's see. Now let's look at the function that we are looking at. Right. So this is the determinant that we are looking at, and just to massage it a little bit, you can do it in several ways, but let's do it like that. So let's first of all multiply by r theta plus I from the right. So this A will get this thing, and this will remain here, but that will cancel with this. Right, because r theta transpose is r minus theta. And they cancel each other. And also now let's conjugate sorry. And now let's write r theta plus I using the notation that we introduced. So V this diagonal d theta v conjugate instead of this part and also here. And now let's conjugate from, let's multiply by v star from the right, v conjugate from the right, and v conjugate from the left and v from the right. It doesn't change the determinant because you can do a cyclic shift, and then it's just I. So you get this expression. Right, so you get a v star here, and this goes away, and here this goes away, and here you get a v. So that's what you have here. And now we just need to stare at it for a second. Now we did enough massage, it's actually apparent what's going on. So this matrix, that I just erased, this matrix, if you think about it for a second, its first two rows depend on theta, but only those, right? Because of the d theta that appears here. In d theta, you have only the first two upper left upper entries that depend on theta. The rest are ones. So only the first two rows here depends on theta. These entries are theta free, and here similarly only the first two columns depend on theta. And you look at the sum of that, and then you take the determinant. So really, you look at the matrix in which only the two rows and two columns has theta appear in there, and when it appears, it's either e to the I theta or e to the minus I theta, or in the cases where in this maybe four or maybe two of them, you have maybe e to the I theta plus e to the minus I theta and so forth, but you don't have higher powers of e to the I theta or e to the minus I theta. And now when you expand the determinant according to the usual determinant, like product using permutations, you know that every summand is a product. It's a product of an element from each row and each column, but only one from each row and one from each column. So you never get something which, you can get an e to the I times e to the I theta times e to the I theta, but not three times of those. So the largest exponent is, in a sense, is e to the e to the 2I theta, and the lowest is e to the minus 2I theta. And that proves the lemma. Good, so that's it. We just proved kind of a remarkable result, I think, that when you walk orthogonal to the structure that you have, this all ones vector, which we'll have, then permutations, which now translates to the symmetric group of the regular simplex, and we really worked with the definition of the regular simplex proof, is as random as R. And the reason really is that that's true for planes, for A2 and O2, and these generate the higher dimensional versions of these groups. So next up, we're going to talk about interlacing, which will enable us to infer something about a particular permutation, how it behaves, if we know the expectation over permutations, which is, in a sense, it's a very strong and non-trivial version of the probabilistic method. Okay.